So now we're going to talk about what some of the things that are happening after the merge. So lots of things are happening after the merge, obviously. There's a lot of improvements around the blockchain security, a lot of application layer stuff, trying to improve ease of use, a lot of improvements around privacy. But the thing that I want to focus on right now is what is our top priority once the merge is finished, which is increasing the Ethereum blockchain's scalability. So why is increasing the Ethereum blockchain's scalability is important? I think there's two ways of looking at it. One is to just do the math and understand how many transactions the Ethereum blockchain can process today, right? So the Ethereum blockchain today, the number is it can process about 20 transactions a second if we're looking at actual transactions that just regular people send on chain today, but it can go up to about 60 per second if we're talking about very small and minimally sized transactions, right? Now, how much can 20 per second or 60 per second actually do? It's good enough for a lot of use cases, right? So one way to look at 20 per second is multiply it and look at the number per year, right? So 20 multiplied by 31.5 million, 630 million transactions per year. So it's enough for everyone in the United States and Europe to, say, register a domain name and update it once a year, but nothing else, right? If you look at payments applications, a lot of the mainstream payment processors, they have TPS numbers of sometimes 1,000 to 10,000, sometimes up to 100,000, or even up to 1 million, right? And if we start looking at other applications like even gaming and non-financial applications on the internet, the kind of TPS that they require is even higher, right? So scaling is important. Another way to look at it is from the point of view of transaction fees, right? So today, transaction fees are still very high. They're much lower than they were 1 or 2 years ago, fortunately, but it still takes somewhere between maybe 50 cents and a few dollars to send a transaction. This is good enough for large-scale financial applications, but it's not good enough for, say, accepting payments for just random, at a coffee shop or for some product on the internet that only costs $10 or $15. So reducing transaction fees is very important. And the only way to reduce transaction fees well, there's two ways to reduce transaction fees. One way is to make Ethereum useless, so nobody wants to use it. Then transaction fees will be very cheap. The other way is only to increase supply, right? To increase the amount of space on the chain so that users and transactions don't have to compete against each other as much. So how are we doing scalability? This is a document that I published about 2 years ago, the Ethereum rollup-centric roadmap. And it's at the time, I think things were really moving in this direction already, right? So I think in a lot of ways, this was kind of more acknowledging what was already happening and well on its way. But the core idea basically is that instead of the Ethereum base layer protocol being responsible for kind of doing all of the scaling by itself, we have this kind of separation of layers, right? Where you have the Ethereum base layer, which provides data space for transactions, for rollups and other applications to store data. And the job of the base layer is to just be open, decentralized, censorship-resistant, and secure, and in the long term as stable as possible. And then you have layer 2 projects that can use the base layer to anchor themselves and provide more scalability and speed on top. So this is the rollup-centric roadmap. Okay. Right, so base chain focuses on providing what we call availability guarantees. So basically, the base chain is a place where people can send transactions that just contain large amounts of data. And rollups use this space of data and put transaction data into that space. And this allows rollups to be this kind of chain inside of a chain that can process a much larger number of transactions. So this is the format, right? So basically, we have this kind of blob data space that's on chain, and rollups need that data space. And the more data space we have, the more transactions we can include. There's two ways to try to optimize this, right? So one way to optimize this is to add more data, to add to the base chain the ability to store and process and verify the availability of more data. The other way to optimize this is to make each transaction take up less data. So we can kind of look at some of these in turn, right? So today in the status quo, a block theoretically can be up to a megabyte in size, but the big problem that we have today is that rollup data has to compete with existing transactions and existing applications for space, right? And so in an actual Ethereum block today, only a small portion of the gas in the block is actually being spent on data for rollups, right? So because rollups have to compete with these existing applications, basically, because using the blockchain indirectly through these layer 2 protocols has to compete with using the blockchain directly as layer 1, it's very expensive and it only gets a small portion of the space on chain, right? So on average, maybe somewhere around 10 to 50 kilobytes in a block. Proto-danksharding, so also known as EIP 4844, right? So this is the probably biggest EIP after the merge that people are working on right now. And the goal basically is to introduce a new transaction type where this new transaction type can store what we call these large blobs of data. And in these blobs of data, you can have a much larger amount of space. So 128 kilobytes in one blob. And into each of these blobs, you can have rollups that can put the data for a very large number of transactions. Now, proto-danksharding is called proto-danksharding because it's the first step. Full danksharding, actually, the picture is a little bit typoed. The full danksharding should not be 1 megabyte because that's proto-danksharding. It should be 16 megabytes, right? So, and in the future, I expect it will go even higher than 16 megabytes, right? So full danksharding is this kind of further extension to the same protocol that allows the chain to include a much larger amount of data. And there's like extra cryptographic magic that's happening to make this possible to run while only allowing each individual node to store and download and check a small portion of all of the data. Right, so this is one way to improve things. The other way to improve things is to reduce the amount of data per transaction that has to go on chain. So the uncompressed, so this is the way that things started. If you look at ERC20 token transfers, so transfers of any token that's not ETH, then a transaction, just a regular Ethereum transaction, sending an ERC20 token requires somewhere about 180 bytes of data on chain. And if you just make a rollup the easy way, and you make a rollup that just like copies the logic of the Ethereum base layer, then you need to put 180 bytes on chain for every one of these transactions. Now, if we want to like try to understand how much efficiency you're gaining by doing this versus just using Ethereum directly, we can try to measure things in gas, right? So in gas today, 180 bytes is going to cost about 180 times 16, so about 2,880 gas. And on layer 1, an ERC20 transfer costs maybe about 50,000 gas. So you're gaining about 20x in this particular case. So it's a significant gain, but in the long term, it's not enough of a gain. So how can we make transactions take up less space? Now, the answer is compression, but this is kind of a cop-out answer because the definition of the word compression is making things take less space. So we need to understand kind of how are we making these transactions take less space. So one simple thing that we can do is just use compression algorithms, right? So the simplest form of compression is what I call 0-byte compression. Basically, anytime you have a string of a large number of zeros, you just replace it with 2 bytes. The first byte tells you how many zeros there are, and the second byte is a 0. Or something approximately like this, right? So this by itself reduces it already to about 154 bytes. Now, you could go a step further and you can use, Snappy or like some other kind of like mainstream compression algorithm, and you lose a little bit more, but probably not enough, right? Now, another thing that we can look at is the signature. Now, signatures are cryptographic, basically random data, and so you might think that signatures are not compressible, right? But there is one thing that we can do with signatures, which is instead of compressing them, we aggregate them. So what does it mean to aggregate signatures, right? Basically, what this means is instead of putting every single transaction signature on chain, we replace all of the signatures with a single cryptographic proof that says all of these signatures exist. Right? So we just replace a huge number of signatures with one proof, and the proof cryptographically proves that a lot of signatures exist. There's different ways of doing this. So BLS aggregation is one that technically inclined people might be familiar with. Ironically enough, people who are less technically inclined but deep into Ethereum lands might understand the aggregation strategy called just make a snark. Which is mathematically much more complex, but people have been blabbing the word snark in people's faces for a few years, so people might know what it is already. Who here has heard of snarks? Okay, good. Yeah, so you could, there's lots of ways to aggregate signatures, right? But the point is, if you replace all of these signatures with just one proof, then you can go down a bit more, go down to 128 bytes. And then if you replace 0-byte compression with theoretically optimal ideal stateless compression, so this is not general purpose compression. It's not like Snappy or gzip or whatever, right? This is a special purpose compression algorithm that's aware of the fact that the thing that you are trying to compress is an Ethereum ERC20 transfer. And so, the algorithm might even have a lot of different special cases that are optimized for the specific use case. So for example, if you want to encode what fee someone pays, you might it might have a specific representation for every whole number of gwei, right? So if your fee is 7 gwei, which as a number is 7 billion, but there might be 1 byte for it, right? So you just try to pack as many really complicated tricks as you can, and you get it down to 75 bytes. Now, ideal stateful compression basically means, well, we don't just do regular compression, we also have a compression algorithm that lets you read the history of the chain, right? So we could be, instead of just saying, compressing numbers into smaller numbers, we actually say, replace an entire address with a pointer to the last time the same address was used, right? So if you do that sort of very fancy stuff, on average, you can get down to about 23 bytes. So this is about a factor of 8 improvements, right? So instead of rollups being a 20x efficiency improvement, rollups become a 160x efficiency improvement. One of the ironic, interesting things, by the way, is that here, the special purpose ZK rollups, so things like loopring, they actually had ideal stateful compression for a very long time. Right? So things like loopring, I believe they've already had 16-byte transactions basically for over a year. But the problem is that people don't want special purpose rollups, people want the EVM, right? And I think one of the fascinating things that's happening with scaling over the next couple of years, and with some of these more complicated technologies and zero-knowledge proofs and compression, is that there aren't really fundamentally new technical problems that are being solved, right? The technical problems have already been solved. The problem is that people want fancy scaling, and people want the existing general purpose EVM at the same time. And it just takes a lot of kind of hard, dirty work trying to make the two fit together. But lots of teams are actually doing this, and people are making a lot of progress. Ding, ding, ding. So proto-danksharding, basically, as I mentioned, right, you have this new concept of a data transaction. So it's a transaction where that transaction contains this extra objects that we call a data blob. And data blobs, they're just blobs of data, right? So you can stick application data into it. You can stick a cat picture into blob data. You can stick a picture of a dinosaur into blob data. Or you can have these protocols called rollups, which use data as a place to put transaction data, and they need this to keep their security. And they basically create these kind of blockchains inside of a blockchain that give Ethereum this Ethereum-like environments that has much more scalability. Now, the next step, full danksharding, right? I mentioned it briefly, but it does involve a bit more cleverness in how blockchains work. So the idea basically is, right, that you have these data transactions, and it introduces this concept of data availability sampling. So the way data availability sampling works is basically instead of a node downloading all of the data in all of the blobs, a node randomly picks a few different chunks of every data blob, and it just verifies a few random chunks. And it knows that if enough of the chunks in the data blob can be found, then with very high probability, enough of the blob has been published that if you want to, you can reconstruct the whole blob, right? So these blobs have this kind of magic cryptographic kind of self-repair property where if you have more than half of the blob, you can always kind of repair it back to 100%, right? If anyone's watched Star Trek, if you remember kind of the Borg cubes and how they can kind of repair themselves, this is like that, but with math. So yay, polynomials. Okay. Next. Right, so a lot of interesting and fancy math, a lot of cryptography, a lot of polynomials, but how far can we go with this, right? So there's two ways that I think we can look at how far we can go here. One of those ways is to look at limits to data availability sampling, right? So data availability sampling is what I call a collaborative verification protocol, right? It is a way in which a community verifies that some chain is, has data which is available, so where the blobs have actually been published, that depends on there being enough people doing the procedure at the same time. If only one person data availability samples, then you can trick that one person. If 10,000 people are data availability sampling, you cannot trick all of them without revealing enough data that everyone can just very quickly reconstruct the blob. So limits to data availability sampling. If each client downloads 50 kilobytes during every slot, and the total data during every slot is n megabytes, then you need to have, on average, 20 times n times maybe a safety factor of 4 clients sampling in order to be safe, right? So if we have 50 kilobytes, and then the total data is going to be, let's say, 16 megabytes, so just like regular danksharding. So plug that into the equation. 80 times 16, so you need about 1,280 clients sampling. Now, if we decide to be brave, and we go with, I don't know, what's the block size on BSV right now? Is it like 512? Do they push it up even higher these days? But I don't know. Let's say we're going to go crazy and try to do 512, right? So 512 megabytes in a slot. You would need 80 times 512 clients. 80 times 512 is 40,960. So over 40,000 clients, so many clients they can't even fit in the stadium, sampling at the same time for the blockchain to be safe, right? So there's this limit to this data availability sampling procedure that basically says that, look, the higher the number goes, the more you need to have this kind of guarantee that a very large number of people are checking the chain at the same time, and if you don't have this property, it's not safe anymore. This is one of the limits to scaling. Another limit to scaling is long-term storage limits, right? So people want a guarantee that they can look up data from the blockchain's history. And they want a guarantee that blockchain history is not just going to be forgotten. Now, the good news is that in order to achieve this guarantee, we do not need to require every single node to store the entire history the way that we do today, right? The way that we do it today is actually quite overkill, right? And EIP 4444 is actually going to kind of separate out the function of being a consensus node from the function of storing the history. So you can store the history if you want, but you don't have to, and validators do not have to. And we can use other decentralized protocols to simultaneously kind of store the history and make sure it's very easy to access. But the problem is that there's still a large amount of data here, and we don't want to make it too difficult for people who really wants to store the entire history to do so if they want to. So n megabytes per slot there's 2.5 million slots per year, so that turns into 2.5 times n terabytes per year. So 16 megabytes per slot turns into 40 terabytes per year. That it requires you to be a hobbyist and it requires you to pay quite a bit of money, but within reach of a hobbyist, right? If we increase n to 512, then we're talking about petabytes per year, and now it becomes like a more institutional thing. So the higher scalability goes, eventually storing all of the history becomes too hard. So these are the two limits. The numbers for danksharding, which by the way can, if you do the math, they can offer somewhere between maybe 20,000 to 100,000 or even more transactions per second with rollups. They are kind of well within the safety margins, but this also can be increased over time. Next. Yeah, so there's still a lot that we can do, right? Now, an interesting thing, we do, I think, need to start thinking about what's going to happen after the scaling transition, right? After the scaling transition, different kinds of things become expensive. So today, reading and writing from the state is expensive, doing computation on chain is expensive, or a bit less expensive, and data is not very expensive. In a rollup, data will be very expensive. If it's a ZK rollup, then snark unfriendly computation will be expensive, and reading and writing from the state will be kind of expensive, but computation is going to be cheap, right? So we are going to be scaling, and a lot of things will become cheaper, but some things will become cheaper than others, and in this post-rollup world, you will still have to care about kind of economizing on your blockchain use, and the way that applications are designed probably will have to change at least somewhat. So how do we get here, right? So 3 big EIPs, EIP 4844, proto-danksharding, first step to danksharding, adding more space on chain. ERC 4337 is account abstraction. I did not talk about this, but that's the ERC that's that will allow Ethereum accounts on rollups and on layer 1 to benefit from saving data through things like BLS aggregation, so you can to really decrease the amount of data that they need. And EIP 4444 is the EIP that kind of separates out being a consensus node from storing history, and so it allows regular nodes to continue to be easy to run even while the blockchain has all of this extra data. So all of this stuff is in progress. Lots of very smart and very hardworking people trying every day to make this happen. And this is all going to create a kind of much more exciting, much more scalable and accessible and cheap blockchain space.